Section 6.1, Power Series and Functions. So in this chapter, we will be talking about a particular type of series, called the power series, quite obviously. And the idea here is that we have an infinite polynomial. We can use a series to represent an infinite polynomial. Now, each of these coefficients here are constants, and so this is a polynomial in terms of x. So an example that's going to come up and be very useful here in a little bit is this right here, this power series. The sum from 1 to infinity of x to the n, which is 1 plus x squared plus x cubed, etc. And this is a geometric series with our ratio being the absolute value of x. And this converges if the absolute value of x is less than 1, because it's geometric, and it diverges if the absolute value of x is greater than or equal to 1. So the formal definition of a power series is this. A power series of the form, or a series of the form, the sum from 1 to infinity of Cn x to the n, which is that infinite polynomial, is a power series centered at x equals 0. Now the reason we say it's centered at x equals 0 is because this is, well, each term has just an x term in there. Okay, as opposed to this second form that we can possibly have, Cn x minus a to the n, which is, we have an x minus a term with varying exponents. So in that case, it is centered at x equals a. It's centered at x equals a. So let's look at these two examples real quick. The power series from 1 to infinity of x to the n over n factorial, that's centered at x equals 0 because it has a term x to the n. That's it. There's no x minus some value. Now, the second one, x minus 2 to the n, well, right away I can tell you that that is centered at 2 because the value 2 would make that term 0. Now, it's worth noting that we actually have to allow for a slight bending of some algebra rules. That is, x to the 0 equals 1 and x minus a to the 0 equals 1, regardless of x and a. Now, this actually does not cause any problems, regardless of what you might think. It actually makes these work out very well, and eventually allows for, in our next section, allows for functions to be represented. Actually, we do that some in this section. It allows for functions to be represented by a series, which has some great properties. All right, so example 3, write out the first few terms of this series and determine C0, C1, C2, and C3. And actually, we'll go a little bit further. All right, so to begin with, we've got if n equals 1. If n equals 1, our term is x squared over 1 factorial, which is just 1. All right, n equals 2. If n equals 2, this will be x to the 4th over 2 factorial, so that is just 2. Okay, if n equals 3, this is x to the 6 over 3 factorial, which is 6. And if n equals 4, this is x to the 8 over 4 factorial, which is 24. All right, now when we go to determine our coefficients, okay, C0, C1, C2, C3, etc. C2, C3, C4, C5, C6, C7, and C8. We'll go ahead and go out that far. What we are looking for is the coefficients on the x to the 0 term, that's C0. Well, in this case, there is no constant term. So that coefficient is 0. There's also no x to the first term. So that coefficient is 0. Our x squared term has a coefficient of 1. There is no cubed term. So we have a 0 for C3. C4 is a 1/2. C5 is a 0. C6 is 1/6. C7 is 0, and C8 is 1/24. That will really come up. This idea of recognizing the coefficients will be very important in once we start looking at Taylor and Maclaurin series. Right, so this is worth noting. All right, convergence of a power series. If we have a power series, then exactly one of these three things will occur. Either the series converges at x equals a, where it's centered, and diverges for x not equal to a. And I'm going to say this in a second, but this means that our r, our radius of convergence, is 0. The series converges for all real numbers, in which case the radius is infinity. Or our third case, there exists a number r greater than 0, such that the series converges if the absolute value of x minus a is less than r, and it diverges if the absolute value of x minus a is greater than r. At the endpoints of that interval, so we will have something kind of like this, negative r to r. That'll be our interval. Now, we're not told what's going to happen at, it'll have something that looks like that. We're not told what will happen at the endpoints themselves, so we have to test those. Now, in all of these cases, really, that number r is the radius of convergence. The set of values where it converges is called the interval of convergence. And I already made a note of that fact. So example 4, x to the n, we said it's geometric, so it converges when the absolute value of x is less than 1. Which means its radius of convergence is 1, and the interval of convergence is -1 to 1. Now, I would have to test the endpoint. So if I evaluate x is -1, then that makes this series here an alternating series. If x is -1, that's an alternating series which diverges. If x is +1, then this is the sum of 1, an infinite sum of 1, so that would be also diverge. So that is why I'm not including -1 and 1 in my interval of convergence. All right, let's look at this one. Find the interval and radius of convergence of x, the sum of x to the n over n factorial. Now, this is not geometric, so we are going to use the ratio test. As a reminder, the ratio test is the limit as n goes to infinity, the absolute value of the n plus 1th term. So in this case, x n plus 1 factorial divided by the nth term, x to the n over n factorial. Now, the ratio test says that if our limit of this ratio here, the absolute value of this ratio, if it is between 0 and 1, including 0 but not including 1, then our series converges. If the limit is greater than 1, then it diverges. And if it is equal to 1, then this is inconclusive. So let's just begin by looking at that limit. All right, well, the n factorial cancels, so we get an n plus 1 left in the denominator. And the x to the n divides out to be x. So I have x over n plus 1, and the absolute value. Now the limit of that is 0. So by the ratio test, okay, this series converges. And since it converges, in general, that means it converges on the interval -infinity to infinity, which makes our radius of convergence infinity. Next, find the interval and radius of convergence of the series n factorial times x to the n. So again, we will appeal to the ratio test. The ratio test turns out to be very helpful with power series, so remember that. This will be the n plus 1th term divided by the nth term Alright, so this is the limit as n goes to infinity of n plus 1 times x. Let's put that back in parentheses. N plus 1 times x. And this limit is infinity. Okay, therefore, by the ratio test, the series diverges. Right, so our ratio, or our radius of convergence, is 0, and it only converges at x equals 0, because if x is 0, then this is the sum of 0. All right, so our interval of convergence, there's really no way to write that when it only converges at one point. I suppose I could write interval of convergence is, it's centered at 0, so 0, but that's really not meaningful, so I'll probably refrain from writing it that way in the future. All right, example 7, and of course check out OpenStax Calculus Volume 2. The link is on the bottom of every page, so please do that. Find the interval and radius of convergence. Again, we will appeal to the ratio test. It's just a really good go-to for all of these. So it's the absolute value of the n plus 1th term. So that will be n plus 2 there. And 3 to the n plus 1. All over x minus 2 to the n over n plus 1, 3 to the n. Okay, so that limit, several things are going to cancel out. We're going to have a 3n and a 3n plus 1, so we'll have a 3 in the denominator. We will have an n plus 1 in the numerator and an n plus 2 in the denominator. And we have just an x term here. Now that limit, because x is, for all intents and purposes, a fixed value, the limit of these two right here, these two terms, the limit there is 1. So the limit overall is x over 3. The question is, when is the absolute value of x minus 3, or x over 3 going to be less than 1? That'll tell us when it converges. Well, I can rearrange that to say the absolute value of x is less than 3. So this converges, this series converges whenever the absolute value of x is less than 3. Oh, I just realized I messed something up there. That'll make a difference. Let's go back here. I wrote just an x there when those canceled out. There's not just an x there. There should be an x minus 2. Okay, so this limit is x minus 2 over 3 absolute value. We still want that to be less than 1, which would mean the absolute value of x minus 2 is less than 3, which is equivalent to saying x minus 2 is between 3 and negative 3, and x is between negative 1 and 5. Okay, so our interval of convergence is between negative 1 and 5. Now what we have to do is evaluate, what if x is negative 1? If x is negative 1, then our series is negative 3 to the n over n plus 1 to the 3n, which is equivalently negative 1 to the n over n plus 1. Now, by the alternating series test, this converges. The sequence, if you ignore the alternating part of that, the 1 over n plus 1, it is decreasing and it is bounded. So this converges. So we will actually include, do that differently, we're going to include that endpoint. Now what if x equals 1? Oh, 5. If x equals 5, this would be saying the sum of 3 to the n over n plus 1 times 3 to the n, or equivalently 1 over n plus 1. Now, by a comparison, by a comparison to 1 over n, okay, by the limit comparison test, this one would diverge. This diverges because the ratio of those two is 1. All right, so we will not include 5. So that means our interval of convergence is -1 to 5, not including 5, but including -1, which makes our r equal to 3. All right, next, number 8, find the interval and radius of convergence of the sum, or the series, x to the n over the square root of n. All right, so our ratio test, x to the n plus 1 over the square root of n plus 1, divided by x to the n over the square root of n. Absolute value of that. And that limit reduces down to, we have the square root of n over the square root of n plus 1. And that would be just an x, absolute value. The limit there is the absolute value of x. That converges when that will be less than 1, which means our interval of convergence is -1 is less than x is less than 1. And we can say our radius of convergence is 1. Now we need to consider our endpoints. So if x equals -1, then that is -1 to the n over the square root of n, which by the alternating series test converges. And again, just notice that that is a decreasing sequence there. It's decreasing and it converges to, and the sequence itself goes to 0, the 1 over the square root of n. So we are going to include -1. If x equals 1, that is 1 over the square root of n, which as a p-series, that diverges. So we will not include 1. So our interval of convergence, we can write that as -1 to 1, not including 1, including -1. All right. Now, we've looked at this already, but it's worth bringing up again. This series, infinite sum of x to the n, is geometric, and that means, by definition of our geometric sequences, how we know what they converge to, this is equal to 1 over 1 minus x, as long as the absolute value of x is less than 1. So that infinite polynomial approaches, or is equal to, as we're saying here, it equals that function as long as the absolute value of x is less than 1. So let's look at the sequence of partial sums. The partial sum S2 is the first one we're going to look at. All right. Well, S2 would be the sum of the first two terms, which would be 1 plus x. Okay. S4 would be the sum of the first four, so 1 plus x squared plus x cubed. And then we'll add the first 6 terms. 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. Now, we want to look at the graphs compared to f of x is 1 over 1 minus x and make an observation. What appears to happen to the approximation Sn, partial sum, as n increases? Well, in blue we have the function 1 over 1 minus x. And each of those we have blue, orange, and then green. And in the interval -1 to 1, which is what we're really concerned about, what appears to be happening as you go from 2 to 4 to 6, the partial sums, as those increase? Well, hopefully it appears to you that they are getting closer. They're sort of bending up as you approach 1. They're getting closer. They're increasing in their rate of change there. And as you get closer to -1, they're actually just pretty good anyways. So they're pretty good approximations. So what appears to happen is that as n goes to infinity, Sn approaches f of x. This is going to turn out to be one of the most important ideas in mathematics. We're doing all of this to get to this point, really, where we have power series and Maclaurin series and Taylor series in particular. All right, so use the fact that the sum of x to the n is 1 over 1 minus x for absolute value of x less than 1 to find the power series for f of x equals 1 over 1 minus x squared, and then find the radius of convergence. All right, so what we are going to do is rewrite the function f of x, 1 minus 1 over x 1 over 1 minus x squared. And how I'm going to rewrite that is actually just to consider this right here. So this I can use is a geometric series, n equals 0 to infinity, of x squared. That's my ratio now to the n, which is equal to the sum from 0 to infinity of x to the 2n. Alright, so that's my power series. That is my power series. But this is only valid for the absolute value of x squared being less than 1, which is equivalent to the absolute value of x being less than 1. So my radius of convergence is 1. There's my power series. Radius of convergence is 1. Find the power series for f of x equals 1 over 1 plus x cubed and find the radius of convergence. Well, we will rewrite f of x in the same way that we have the 1 over 1 minus x. 1 over 1 minus negative x cubed. Verify, make sure you agree with that. All right, and this is a geometric sum from n equals 0 to infinity of negative x cubed to the n, which I'm going to write as negative 1 to the n, x to the 3n. Now, this is only valid if the absolute value of negative x cubed is less than 1. Going back to this idea right here. Well, that is equivalent to the absolute value of x is less than 1. So our radius of convergence is 1. This didn't ask for it, but our interval is negative 1 to 1. And there is our power series. Either of those are equivalent forms. Number 13. Find the power series for this function, x squared over 4 minus x squared. This one's going to take a little bit more doing. First, I'm going to factor out an x squared. And in fact, I'm going to take out an x squared over 4. 1 over 1 minus x squared over 4. Double check that. Hopefully you agree with that. Now, this is very similar to our geometric formula. So I'm going to leave this x squared over 4 out and write the power series for what is remaining. That is x squared over 4 to the n. Okay. By doing that, this is only valid, I should probably note this, if the absolute value of x squared over 4 is less than 1. Let's go ahead and rearrange this. That'd be the absolute value of x squared being less than 4, and taking the square root, because we can do that. Absolute value of x is less than 2. All right, so our radius of convergence is 2, interval -2 to 2. I don't know anything about the endpoint, so I'm leaving it there. All right, so I'm going to go ahead and rewrite this a little bit differently. That will be the sum from n equals 0. Whoops, left that off. 0 to infinity, and that'll be x to the 2n plus 2, combining these together, and 4 to the n plus 1. Now, what we are saying then is the function x squared over 4 minus x squared is equal to, and here are the first few terms, x squared over 4 plus x to the 4th over 4 squared plus x to the 6th over 4 cubed plus, if the absolute value is of x is less than 2. We're saying that those two are equal. Last question that's very similar to this. Find the power series for f of x equals x cubed over 2 minus x. All right, let's begin by rearranging that. We'll factor out an x cubed over 2, because I want it to be a 1 minus something in the denominator and a 1 in the numerator. So if I factor out the 2, that's 1 minus x over 2. Now again, that looks very much like our geometric formula. So n equals 0 to infinity. I'll leave the x cubed over 2 here. And that would be x over 2 to the n. As long as the absolute value of x over 2 is less than 1, which would imply absolute value of x is less than 2. Alright, so let's go ahead and rewrite this. That is the sum of n equals 0 to infinity of x to the n plus 3 over 2 to the n plus 1. Okay, again, for absolute value of x less than 2. Now what we are saying again is that x cubed over 2 minus x is equal to x cubed over 2 plus x to the 4th over 2 squared plus x to the 5th over 2 cubed plus etc. As long as the absolute value of x is less than 2. Alright, that brings us to the end of this section over power series and the functions that we can kind of relate to them, these rational functions. Now, it's a good idea to go back and check this out again. Make sure that everything makes sense. If not, ask questions. Alright, that's 6.1.